Welcome back, everyone, to the eCoreAcademy e-learning platform. Today, my name is AJay Raj, back with yet another geometry video for you all, and today's lesson topic is all about chords and arcs. Now, before we jump into today's lesson, please make sure to smash that subscribe button, hit that like button on this video, as well as turning on post notifications by hitting that little bell icon right next to that subscribe button. All three of those things are very greatly appreciated, and also, please utilize the comment section down below. Add any of your constructive feedback and any of your comments that you want to add in response to our videos or about our e-learning platform in general, and we'll be gladly there to respond and display all of your comments. As I was saying, our topic of focus is going to be chords and arcs, and this topic, like I said previously in my previous video, is going to be a build-up off of tangents and circles. So these two lessons are going to be interconnected and very well correlated, because a lot of the topics that they share are going to correlate as well. And of course, this is to start off, this is the second lesson on our new unit. It's a larger unit called Circles and Conic Sections, and chords and arcs will be specifically applying to our circles and relating to, tangents, secants, and chords, like I said previously in my previous video. I'm going to be going in depth with chords and then introducing arcs, showing you some similarities and some theorems that go along with each one in relation to circles. And then later on, I'll be correlating tangents, secants, chords, arcs, all into a separate video with higher level thinking and different types of theorems that you'll be coming across in geometry more commonly. But for the theme and purpose of today's lesson, we're going to discover what are chords and arcs and how exactly do they correlate with circles and tangent theorems. So not only am I going to correlate them amongst each other and with circles, I'm also going to correlate them with tangent theorems, and I'm going to show you exactly what they are now. So let's look at chords and arcs part 1, and let's look at all about chords. So I did introduce chords in my previous video, but now let's go into depth and give it a bit more of a more formal introduction. So a line is a collection of points in a straight path. We know that because it's a line has no curvature to it, and it's one-dimensional figure. It's a one-dimensional figure that goes in a straight path, and it goes on for an infinite amount of length, so you cannot calculate its length, or its endpoints are non-existent. And a line segment is a part of a line, so a line segment is a part of a line, a snippet of a line that has endpoints to it, and you can measure its length, so it has a definite length and not an infinite one. And a line segment is a part of a line, but has inclusive points / values with its endpoints, meaning a line segment is going to be considered a part of any line that goes for an infinite amount of length given on that plane. And a line segment is going to share some points with that line segment, with that line, but some of those points, well, 2 of those points are going to be its endpoints, which define it and give it its exact location. And if a line intersects a circle in 2 points, so this is our definition of a chord, we're going to get into the definition of a chord and its underlying characteristic of being a line segment. But if a line intersects a circle in 2 points, then that portion of the line with endpoints on the circle, which is our line segment of a chord, it's both a line segment and a chord. So if you take a line, and you intersect it, goes on the interior of a circle, and basically what you're doing is all external parts of that line, if you just snip it off, then you'll have 2 endpoints that are on the actual circle, and you'll have a line segment formed by both of them located on the interior, and that's either your line segment located on a circle, or more formally known as your chord. Chords and arcs part 2, let's look at identification and types of chords. So just to give you by the book definition, a chord is a line segment that connects any 2 points on a circle, and it's always located on the interior, and it's identified by endpoints, just like any line segment. So I'll show you what that means after this. So diameters are chords, but not all chords are diameters. That's very important to notice. So if you have a diameter, then it's automatically going to be a chord. And by chance, a chord can be a diameter, but not all chords are going to be your diameters. That's the fact that diameters have to pass through the center of the circle, and it has to go through the entirely across your given circle. That's unlike chords, because not all chords have to pass through the center. That's not an identification of a chord. It can, but it's not necessarily going to. However, diameter is best known chord because it's also the largest possible chord, because it goes across the entire span of the circle. as it goes across the entire span of this circle, and it hits through the central point. So I'll do a little practice here with you. So if we look at line segment PQ intersecting this circle O, we're going to try and identify all of these line segments as either diameters or chords, or both. So a diameter is automatically chords, so we'll just do diameters and chords. So let's look here. So I'll make these two columns over here. So chords and diameters. And notice a diameter is automatically a chord. We're just looking for chords that are not diameters here. Okay, so let's look at line segment PQ. Now we know that line segments are identified by their two endpoints. So this is how you'd write a line segment. You put a line here, like that line segment, because it doesn't have arrows, so it doesn't indicate rays or lines, so it's going to be a line segment. And then you write your actual endpoints here to identify the direction of your line segment, where it's going from left to right, and of course its endpoints to identify which line segment you're talking about. So if we look at line PQ, it obviously does not pass through our center here at O, so it's going to be a chord because it does have 2 points on the circle and it's a line segment. It's going to be line segment PQ. And then for diameter, let's look at AB. AB deliberately passes through the center and it's much larger than PQ, so we can assume that it is a diameter. So AB. And then finally we have OC. OC obviously does pass, does have a point on the center, but it does not pass through the center and connect to an opposite side. This is your radius here. So this is technically not going to be considered either. So OC is considered neither, so we're not going to include it in this diagram here. Radius is its own calculation. The reason being for that is the fact that we don't have something, that can actually that a radius can actually be classified under is because radii are unique to a circle. Radii automatically creates your diameter because if you know your radius, it's just double that to get diameter. So it's its unique property, and it basically identifies any unique properties of circles compared to any other polygons in general, any polygons in general. Now let's move on to chords and arcs part 3, and let's look at arcs now. So all about arcs. So an arc, definition of an arc is a connected section of the circumference of a circle identified by the points that create it. I'll explain that. So arcs are enlarged replications of their central angles as they are consistent with the same angle measures. So an arc is basically something that's identified by angle measures, but in degrees. So we can automatically assume that an arc is most likely going to be some sort of curvature. And since we're referring to circles, we can automatically infer that it's going to be a part of the circle, meaning the outer edge or the circumference, that perimeteral area of that circle. It's going to be some sort of snippet of it. And that's exactly what it is. If we look here, we have our line segment here. This is going to be your chord. And then right here, this is going to be your arc, part of focus here. So we look at this circle here, we see this highlighted blue arc here. That's just a part of the exterior of your circle. That's all it is. It's an arc of your circle. It's taking some part of your circumference of your circle and basically identifying it. And the way that an arc is identified is you take its endpoints. Say, for example, you have endpoint A and B. And it's identified by its endpoints, and it's classified by this. It's just an arc with AB moving from left to right. And then this is a sector. It's when you have an arc here, as shown. A sector is always going to be created after an arc is created. So if you see this arc over here on the side, you see that arc is identified here. And a sector is just basically created when you have two radii on your circle, basically intersecting both endpoints of your arc, and that's basically a piece of the area of your circle, and it's most likely it's judged by your central angle. And I'll explain to you what your central angle is, but an arc is identified by the central angle, and it's measured in degrees. Chords and arcs part 4. Let's look at the different types of arcs. So a minor arc is an arc that is smaller than a semicircle, and it's identified by the points that confine it. Like I showed you before, if you have AB as your endpoints of your arc, that's going to be arc AB with that little curvature at the top. And then your major arc is an arc that is larger than a semicircle. So a semicircle is basically what's halfway at 180 degrees, basically saying halfway around your circle. Minor arc is less than halfway, less than 180 degrees. Major arc is going to be larger than that, so it's going to be the inverse. And And it's I'm just trying to say here as a little PS here. It says that major arcs are congruent, or arcs in general are congruent if they are on congruent circles and are of congruent measures / continuous. So what that basically is saying, that if you have two arcs, on two congruent circles, and both of those arcs have the same measure in degrees, that means both arcs are going to be congruent and congruent measures. And also, your arc can be measured by a linear unit, such as a degree mark, because it's continuous, meaning we have a definite point, a definite fraction of your circle given. That's why. Unlike a line, it's continuous, so you cannot identify it. But say, for example, if you have a line segment on a line, you can identify it with linear units. Same thing with the circle and arc. As you can see here, this is your what I just wanted to show you is basically what I'm trying to say here is if you have a minor arc shown, whenever you have an arc consistent on your circle, whenever you make an arc, you're going to actually have two arcs. Once you make your first arc, you've already identified that that's our arc of focus. But once you make that first arc, you're splitting the circle up into two different arcs, making one arc here, such as this minor arc here, AB here. That's your only focus here. But what about this whole entire other arc that goes around the entirety of the circle? This other arc that goes around the whole circle. What about that one? Well, that's also another arc. And the key thing about this is that if you have a minor arc and that's your arc of focus, then that means the other arc is going to be a major arc. It's going to be larger than your minor arc, and it's going to be greater than 180 degrees. And then we'll also have special case scenarios with their semicircles, in which they'll be equal measures, and both arcs will be semicircles. So chords and arcs part 5, different types of arcs continued, and that's what I was saying, semicircle. An arc that has endpoints that are also the endpoints of the diameter. So if you have the endpoints of a diameter, then that means it's basically just going to be half the circle. So it's going to be halfway across the circle. That arc is going to be halfway and halfway across, and it's going to equal 180 degrees in measure. And the measure of an arc is either in degrees or radians. I have not introduced radians yet, but I just want to put that out there. Maybe you're already familiar with it coming into this lesson, but I will be teaching that when we go over trigonometric ratios. And I will also refer to it later on in this unit as well. But it replicates an angle. Basically, it replicates your central angle located in the center of your circle, which is 360 degrees. And it's always going to equal 180 degrees. You'll have two of them. And it can be identified by a maximum of 3 points. So any arc can be identified by 2 points at its endpoint, or 3 points, two endpoints and 1 point that's located somewhere along the center of the arc. So as you can see here, this is your diameter CB of circle O, and we're connecting. Let's focus on the blue one here. So we're going to connect the endpoints of CB. Once you've connected that, you're also forming another one connecting CB as well on the opposite side, semicircles, and both are going to be equal to 180 degrees, and both add to 360 degrees, the measure of your central angle of your circle, of any circle. Chords and arcs part 6. Let's look at central and inscribed angles. Let's look at what I mean by central angles and how they actually connect with and correlate with chords and arcs, and also how they correlate with circles in general. So a central angle is an angle whose vertex is the center of the circle and whose legs are radii. Keep in mind, an angle is formed by two kinds of lines intersecting. That can be line segments, or rays. In this case, it's going to be line segments. And it's basically the angle that when you take the center of your circle and you draw any radii outwards, you're going to have an angle formed in between those two radii, two or more radii to have multiple angles. And an inscribed angle is an angle that has its vertex on the circle, meaning on the edge of the circle, and its sides are chords of the circle. And those two chords will intersect to form that inscribed angle. And these are examples. So if we look at this center O of circle O, we have the center here. And as you can see, we have two radii basically going from OC and OA. They're both your two radii going from the center of the circle. So this angle right here will be a central angle, basically just located in the center. Central angle. Okay, and this is going to be your inscribed angle because it has a point on its vertex is on the circle and two chords are creating it, so it's going to be inscribed. And this is also going to be inscribed angle A, and so is angle C. There we go. Now let's look at the theorems that basically correlate these together. So this is theorems part 1, chord and arc theorems. So let's look at our theorem number 1, and it states that the degree measure of a minor arc is a measure of its central angle, and the formula for length, which I will show you soon. So let me just explain what I mean by the degree measure of a minor arc is the same measure of its central angle. So basically what it's stating is that if you have, your central angle here, whenever you're forming some sort of arc, like I said, you're going to have a sector. You're going to have a sector by when your radii basically connect the endpoints of your circle and they meet at your center here. And this angle formed here, the central angle formed here, say for example it's 78 degrees. The arc length will also be 78 degrees as well. That's all it's stating there. And basically what the formula for calculating the length of it, since we know that an arc is not going to be a continuous part of a circle, we can identify by linear units. And because we also know the circumference of a circle, it's just going to be a fraction form of that. So what we're going to do is we're going to utilize our central angle because our central angle is automatically the angle of the arc length. So central angle in geometry is actually going to be theta. Theta looks like this. It's going to be like a 0 with a little curvature here. It's going to be arc here and curvature here, and that equals theta. Now the equation will be 300 theta. It's going to be more of like a 0, not an O. Theta divided by 360 times 2 pi r. Now all this is doing is it's taking theta divided by 360 degrees. It's taking your central angle divided by 360 degrees to see what fraction of the circle is actually being taken up. And then you're just going to multiply it by your circumference. Because remember, your circumference is actually representing the entire length of the circle. So you're just multiplying it by a fraction to get the smaller portion of your arc here. And you'll just plug in these values to discover that utilizing this equation. But I will utilize that later on in my next videos. Don't want to get too jumped ahead because I want to take my time with this and help you guys really understand it. Let's look at theorems part 2, chord and arc theorems continued. Theorem number 2 states that in a circle or in congruent circles, two minor arcs are congruent only if the corresponding chords are congruent. So if you're automatically given, congruent circles, or if you're given two different minor arcs on the same circle, the only way that your minor arcs are going to be identified as congruent if you don't know the measures of your arcs, either in linear units or in degrees, then all you need to do is just discover if the corresponding chords are congruent. Meaning, if you look here, you can see that AO here, this line here, is actually going to correlate with this line here, OQ. And then this line here, BO, is going to correlate with this line here, PO. And if they have the same exact length, then that means that both arcs are going to be congruent. So QA and PQ will be congruent if that is proved. Very straightforward. Theorems part 3, chord and arc theorems continued. Theorem number 3 states that in a circle or in congruent circles, two chords are congruent only if they're equidistant from the center. So all it's saying is basically if you have, chords, or if you have radii in this case, which I will draw across. So I'll draw, say for example, a chord like a diameter here and maybe another diameter here. And all it's saying is if all endpoints, corresponding endpoints of each point on the chord is the same distance from the center, that means both chords are going to be equivalent. And finally, for theorems part 4, chord and arc theorems continued. Theorem number 4 states that in a circle, a radius is perpendicular to a chord if and only if it bisects it. So I did refer to this in my previous video. I'm just going to go over it again. And I stated this in tangents and circles, went into depth with it as well. But basically what it's saying is if you have your radius of your given circle, so this is circle O, center is at O, and a radius is any line that goes from the center and connects to any point on the circle, and it's any point on the circle is always the same distance from the center through the radius. And this OC, this radius here, is intersecting this chord here, AB. So as you can see here, OC is your radius, AB is your chord. And when they intersect, they will actually form a 90-degree angle. Remember, you have infinite radii that can be formed on a given circle, but a radii is there's always going to be one radii that's going to be perpendicular to any chord. And when they are perpendicular, and when you find what that radii is and the location, and you can actually draw that out, give a visual of it, it'll intersect at a 90-degree angle, and also will be a perpendicular bisector. And that bisector splits into two halves and intersects at a 90-degree angle. Just as simple as that. You can utilize that if you know the value of AB, then you'll know the value of AP and PB if you know that you have a radii that's intersecting at 90 degrees. All right, everyone, so that'll be it for today's video. I hope you all enjoyed. This has been the eCoreAcademy e-learning platform today. Before you leave, please make sure to like and subscribe down below and hit that post notification bell so you don't miss out on any of our latest uploads. Please check out our website at eCoreAcademy.org. There we have full unlocked access to what we as an online e-learning platform actually offer. We have full unlocked access there to our quizzes, worksheets, integrated note sheets, and videos organized into course studies and under their separate lessons with progress checks and other events, tips and tricks that are added bonus to our YouTube channel. So go check that out. Link is in the description below. And all you need to do is make an account and sign up for free. And also, if you have any questions, email us at eCoreAcademy@gmail.com. Reach out to us with any questions, or if you just want to talk to us, we'll gladly reply back as soon as possible. And finally, check out all of our socials in the description box below: Facebook, Twitter, and Instagram. Our full link down there is in the description box, and see what kind of content we have there and use our mediums to share all of our videos. Once again, everyone, this has been AJ. I had a blast making this video, and I hope you guys enjoyed. And I will see you guys in the next one. Peace.